Welcome to the Deep Dive. Today we're tackling a fascinating piece of research, analyzing sequential activity and travel decisions with interpretable deep inverse reinforcement learning. Now that's a mouthful, I know, but at its heart, this paper is really about understanding the hidden logic behind our daily routines. You know, how we move around our cities.
Yeah.
It feels like a crucial step forward in how we model human behavior using, well, machine learning.
Absolutely. For years, the way we've thought about travel demand has mostly been looking at individual trips.
Right. Trip-based models.
Exactly. But think about your own day. A trip to the grocery store isn't isolated, it's part of a sequence. Maybe you went to work first, maybe you'll go home afterwards.
Yeah, it's connected.
This paper really recognizes that our daily movements are driven by these connected chains of activities.
Exactly. So this research shifts the focus to these activity-based models, looking at the bigger picture of our day. And to analyze these sequences, they're using a pretty powerful technique called deep inverse reinforcement learning, or DIR.
Right. We've touched on reinforcement learning before, training AI through rewards, inverse reinforcement learning. Well, it's kind of like being a detective, isn't it?
That's a good way to put it. Yeah. We see the actions, the behavior, and we try to figure out the underlying motivations or the rewards that cause them.
Okay.
And DIRL uses these sophisticated deep neural networks to estimate these really complex reward systems and the resulting behaviors. And it's actually become very good at predicting what people will do next.
But there's a catch.
Precisely. The authors here noticed a key blind spot. While we can often predict what people will do, we're often still missing a clear understanding of why they do it.
And that's where the interpretable part of the title comes in.
Exactly.
This framework, it seems, aims to bridge that gap between the, let's say, data-driven power of machine learning and the more theory-based models we've traditionally used to understand behavior.
So our goal today is to really unpack how this framework learns and, crucially, how it lets us understand both the patterns in our behavior and the underlying preferences driving them. So what's the core contribution here? What's the big idea?
Well, the real breakthrough this paper, I think, is this novel interpretable DIRL framework. It allows us to really dig into why we make the daily activity and travel choices we do.
Okay.
They've adapted something called adversarial inverse reinforcement learning, or ARL.
ARL, right.
Yeah, using deep learning to basically infer these reward and policy functions just from observing how people behave.
So ARL is like a competition between two AI systems. One tries to generate realistic day-to-day patterns.
Yeah, and the other one tries to tell the difference between those generated patterns and, real-world data.
And in doing that, they kind of uncover the hidden rewards guiding our actions.
That's a great way to put it, yeah. Think of it like a really sophisticated game of spot the fake. One AI, the generator, tries to create realistic travel patterns, and another, the discriminator, acts as a very discerning critic, constantly learning what real behavior looks like. This back and forth helps them both understand the underlying rules, sort of our travel decisions.
Right.
But the real innovation here, the key thing, is the focus on making those rules understandable. They don't just want a better prediction. They want to know why those predictions are happening.
How do they achieve that?
They do it by, using a simpler, more transparent model, a surrogate model, to interpret the complex behavior patterns learned by the main AI.
Oh, okay.
And also by carefully analyzing the short-term satisfaction or reward and the long-term value or return that the AI associates with different choices and patterns.
And why is this ability to understand the why such a game changer? Why does interpretability matter so much here?
Oh, it's huge. Especially for anyone involved in, shaping our cities and transportation systems, urban planners, engineers.
Right.
If we can truly understand the motivations behind people's activity and travel choices, we can design much more effective policies and infrastructure.
So instead of just guessing how people might react.
Exactly. Instead of guessing how people will react to, say, a new bus line or a change in parking fees, we can actually anticipate their responses much better. We can design interventions that are much more likely to achieve our goals, whether that's reducing congestion or promoting public transport.
That makes a lot of sense. So how do they actually model our daily decision-making? How do they structure it so this AI can learn from it?
They use a concept called a Markov decision process, or MDP.
Okay, MDP.
Think of it as a sequence of states and actions that unfold over your day, like steps in a process.
Okay, like a board game.
Sort of, yeah.
Yeah.
Imagine your morning routine. The MDP might see waking up as one state, and then making coffee or checking email, as potential actions you could take from that state.
Get it.
Each action leads to a new state. And the model tries to figure out the probabilities of you choosing each possible action at each point in your day.
And what defines a state in this context? Is it just the time?
It's a bit more complex than that. The state at any given moment is defined by several things. The current time of day, definitely, but also what you're currently doing, your activity, how long you've been doing it, how many activities you've done so far that day, and maybe how long it's been since you were last at home.
Okay, that gives a pretty rich picture of where you are in your day's sequence. And what are the possible actions within this model?
So the actions are essentially the next thing you might choose to do.
Like going home.
Yeah, going home, heading to work or school, doing some shopping, or engaging in other kinds of activities. Importantly, they also include travel itself as a separate action.
So travel isn't just assumed, it's an explicit choice.
Exactly. It acts as a necessary transition step to get between two different non-home activities. You can't just magically appear somewhere else.
Makes sense.
And they use what they call action masks, too. These are basically rules that say, okay, you can't just jump from, say, work straight to the shop without the travel action in between.
Like in that board game analogy, you have to follow the defined moves. You can't just teleport.
Precisely. It keeps the sequences realistic.
Okay. And the reward function, they're trying to figure out, what does that represent in the context of our daily lives? What's the reward for going to work, for example?
Well, the reward function tries to capture the expected benefit or satisfaction an individual gets from taking a specific action in a particular situation.
Okay.
And it's personalized, too. It takes into account their individual characteristics, things like age, income, occupation, that sort of thing.
And the policy function.
The policy function then tells us the likelihood, the probability of that specific person choosing each possible action given their current state.
So they use this DIRL framework we mentioned with its generator and discriminator to learn both these reward and policy functions. How does the deep learning part actually enable this?
Right, so the generator is a deep neural network. Its job is to learn a strategy that's the policy for creating realistic sequences of activities and travel.
Trying to mimic real human days.
Exactly. And the discriminator is another deep neural network that learns to distinguish between these AI-generated sequences and the real-world data they're trained on.
The spot the fake part.
Yeah. And the reward function it learns is actually designed to be stable, even if the overall patterns of behavior change over time. It separates the immediate reward from other factors.
And the policy network itself, how is it built?
It uses mathematical representations, embeddings, to handle the different categories in the state, like activity type, and also the personal characteristics.
Okay.
And it normalizes the continuous data, like time or duration, before feeding it all into a standard feed-forward neural network. The output is then a probability distribution over all the possible next activities, respecting those action masks we talked about.
And how do these two networks, the generator and the discriminator, actually learn from each other? Is it just trial and error?
It's more like a competition that drives improvement. They learn by competing, essentially.
Yeah.
The discriminator gets better and better at telling real data from generated data.
Right.
And the generator, in turn, has to get better at producing more realistic data that can fool the discriminator. They use a sophisticated training technique, an optimization algorithm called proximal policy optimization, or PPO, to fine-tune the generator's policy during this whole process.
Okay, all right. So they've got this powerful DIRL model trained up. It's good at predicting. Now, for the really crucial part, how do they actually make sense of what this complex system has learned about our behavior? How do they interpret it?
Yeah, this is key, because these deep neural networks can be a bit like black boxes, right?
Definitely.
So for the policy function, the behavior part, they use a really clever technique called knowledge distillation.
Knowledge distillation, what's that?
Essentially, they train a simpler, more inherently interpretable model.
Okay.
In this case, they used a multinomial logit model, an MNL.
Yeah.
It's common in travel modeling.
3MNL.
And they train this simpler model using both the actual observed choices people made and the probabilities predicted by the complex DIRL model. It's like the DIRL model acts as a teacher for the simpler MNL model.
Ah, I see. So the complex model sort of transfers its knowledge to the simpler, understandable one.
Exactly. By then analyzing the coefficients, the parameters of this simpler MNL model, they can start to understand the underlying behavioral tendencies that the big DIRL model originally identified.
That's a really smart way to peek inside the black box, isn't it? The complex model teaches the simpler one its insights. And what about interpreting the reward function itself? How do they understand our preferences?
right? For the reward function, they take the real-world activity travel sequences from the data and use the trained reward network, the discriminator part of ARL, to assign a reward value to each step, each decision in that sequence.
So you can see the immediate payoff for choosing, say, travel versus stay home.
Precisely. By looking at these reward sequences, they can analyze the immediate satisfaction or dissatisfaction associated with each decision. But, maybe more interestingly, they also calculate the total expected future reward for entire activity patterns.
The long-term value.
Exactly. It gives them a sense of the overall value or preference the model has learned for different ways of structuring your day. A commute pattern versus a stay-at-home pattern, for example.
Okay.
And they even take it a step further. They use clustering techniques, like K-beans, to group individuals who show similar reward patterns over their day.
So identifying different types of decision makers.
That's the idea. Identifying different groups based purely on their inferred preferences as captured by the reward function.
Fascinating. So they tested this whole framework using real travel survey data from Singapore, right? What did they find? Did it work?
Yeah, they used a pretty standard data set from Singapore.
Yeah.
And the results were actually quite impressive.
Oh, yeah.
Their interpretable DIRL framework significantly outperformed the baseline models they compared it against.
Which were what?
Things like basic statistical models, like a Markov chain or a standard MNL, and even a common machine learning approach called behavior cloning.
Okay.
The DIRL model was better across different metrics. Prediction accuracy, how similar the generated sequences were to real ones, using things like edit distance and BLEU scores.
So focusing on interpretability didn't hurt the prediction power.
Not at all. In fact, it seemed to lead to better, more robust models. And interestingly, that simpler MNL model, when trained using the insights from the DIRL policy network, that knowledge distillation step, it also showed improved prediction accuracy compared to an MNL trained just on the raw data. It really demonstrated the effectiveness of transferring that learned knowledge.
That's great. Okay, so it predicts well. What about the interpretation side? Did they uncover some meaningful insights into how we actually behave?
Absolutely. That was the main goal, right?
Right.
When they looked at the coefficients of that simpler, interpretable MNL model that learned from the DIRL policy, they found some very intuitive behavioral patterns. But now they were quantified by the data.
Like what?
Well, for example, people showed a strong tendency to just continue whatever they were currently doing. Inertia, basically, especially if it was being at home, work, or school.
Makes sense.
Travel was much more likely to happen after someone had finished an other activity, suggesting it often serves as that transition between different types of destinations.
Okay.
They also saw really clear time-of-day effects influencing activity choices, which, lines up perfectly with typical work and school schedules.
Sure.
And things like, the longer you stay somewhere, the more likely you are to leave to travel next.
Right. Diminishing returns, maybe.
Perhaps. And the more activities someone had already done in a day, the higher the chance they would choose to head back home next. Sort of like a daily budget for activities.
Yeah, these all seem to make logical sense, but it's powerful to see them emerge directly from the data via the model.
Exactly. It confirms and quantifies things we might intuitively understand about daily routines, grounding these behavioral models firmly in observed data. That's a big strength of DIRL here.
What about how our personal characteristics influence these choices? Did the model pick up on that?
Oh, definitely. Those played a significant role, as you'd expect. They found that factors like age, gender, income, employment status, they all influenced activity choices in understandable ways.
For instance,
homemakers were more likely to stay home, students were more likely to choose school during school hours, and income levels affected the likelihood of engaging in work and even school-related activities.
Okay. And shifting to the preferences side, what did the analysis of the reward functions tell us?
That was also really revealing. They found, for example, that the act of transitioning to travel generally had the lowest immediate reward.
So we don't really like traveling intrinsically.
Well, maybe it quantifies our inherent desire to be somewhere rather than the process of getting there. Is that a fair summary?
Yeah, I think so. The destination is the goal, not the journey itself, usually.
Right. And the reward associated with an activity like being at work wasn't static. It actually changed depending on how long someone had been doing it.
How so?
It often initially increased, maybe as you settle in, but then it tended to decrease after a while.
Right.
It suggests there's sort of an optimal or preferred duration for different activities.
Interesting.
And overall, activities like home, work, and education generally had higher average rewards compared to other miscellaneous activities, and, of course, travel.
Okay. And you mentioned clustering people based on rewards. What did that show?
Yeah, that clustering based on the reward sequences identified some distinct types of daily planners. They found groups corresponding to, like, regular commuters, regular school attendees, people who tend to combine work or school with other activities, and then groups that looked more like homemakers or retirees with different kinds of morning routines.
Wow. So the model isn't just seeing a generic traveler, it's identifying these distinct sort of tribes of travelers, each with different underlying motivations or preferences.
Exactly. That's incredibly powerful for understanding the diverse needs and behaviors within a city's population.
That is fascinating. And what about the long-term value? Did certain patterns seem more rewarding overall?
Yes, the long-term reward analysis, summing up the rewards over a whole day, indicated that consistent, regular activity patterns, like the typical school day or commuting to work day, were associated with higher overall accumulated rewards according to the model.
And less regular patterns.
More variable patterns, which were often seen in the data for, say, homemakers or older individuals or those with lower incomes, tended to have lower calculated long-term rewards.
That raises some interesting questions, doesn't it, about how we, or maybe the model reflecting societal structures, value different types of daily engagement.
It really does. It's an intriguing finding.
Now, this research obviously doesn't exist in a vacuum. It builds upon a pretty rich history of trying to understand travel behavior using quantitative methods. Could you maybe give us a quick sort of historical context? How did we get here?
Certainly. Yeah, the field has evolved quite a bit. Early attempts to model travel, going way back, were often based on very simple rules and looked at aggregate data. The total number of trips between Zone A and Zone B in a city.
Very macro level.
Very macro. And pretty limited in their ability to capture the complexities of why individuals make the choices they do.
Right.
Over time, more sophisticated statistical models emerged. You had these utility-based models, often based on the economic idea that people make choices to maximize their utility or satisfaction.
Discrete choice models and things like that.
Exactly. Those were a significant improvement, definitely. But they often relied on some fairly strong, simplifying assumptions about how people weigh different factors. And they could struggle sometimes with the interconnectedness of our daily activities, that sequential nature we talked about earlier. More recently, of course, the rise of machine learning has provided powerful new tools for analyzing these huge data sets of travel behavior we now have access to.
But with a trade-off, perhaps?
Well, often, yeah. Many of these data-driven approaches, while they became excellent at prediction, often lacked transparency. They were black boxes. We could see the predictions, but not necessarily understand the underlying reasons why the model made them.
Which brings us back to IRL.
Exactly. Inverse reinforcement learning, and now specifically interpretable deep IRL, like in this paper, represents a really significant step forward. It aims to bridge that gap, combining the predictive power of machine learning with the explanatory insights we value from behavioral theory. There's even a theoretical link between IRL and some of those older dynamic discrete choice models.
So it's like we've moved from simply counting trips to trying to model choices with utility to now using AI to learn those underlying preferences directly from behavior and, importantly, making it understandable.
That's a great summary of the progression, yeah. And this paper specifically tackles that challenge of interpretability within deep IRL, which, as they point out, has been a largely unexplored area despite DRL's success in pure prediction tasks.
They're making these powerful models more transparent.
And hopefully more useful for understanding the why behind our activity travel choices, not just the what.
Okay. So to just summarize the core value of this research for our listeners, what's the main takeaway?
I'd say the key contribution is really a new interpretable way to use deep learning to understand not just what activity travel decisions people make, but also the underlying preferences, the rewards that seem to drive those decisions.
And the methods they use?
The use of knowledge distillation stands out as a clever method for extracting understandable insights from these complex AI models.
Right, teaching the simple model.
Exactly. And analyzing both the short-term rewards and the long-term returns provides a much richer understanding of the value we, or at least the model, associate with different daily patterns.
And it confirms the role of demographics.
Yeah, it clearly highlights the significant influence of personal characteristics on our behavior, and importantly, it demonstrates a data-driven way to identify different types of activity planners based on their inferred preferences.
Okay, great summary. Now, as we often do in our deep dives, let's move into the novel notions segment. Thinking beyond the paper itself, what are some potential future directions, or maybe even slightly speculative research ideas that this work sparks for you.
Okay, yeah. Building on this core insight of understanding individual preferences, imagine a future where urban planning becomes truly personalized.
Personalized planning, how so?
Well, we could leverage these interpretable DIRL models, maybe trained on individual level mobility data, respecting privacy, of course.
Of course.
Combine that deep understanding of individual preferences from DIRL with the kind of personalized recommendation systems we see everywhere now, like in e-commerce or streaming services.
So instead of broad one-size-fits-all policies, we could have interventions tailored based on someone's specific travel behavior profile.
Precisely. Think about policy interventions, like, say, public transport subsidies or maybe congestion pricing. They could potentially be dynamically adjusted for individuals based on their predicted behavioral responses and their underlying reward structures learned by the DIRL model.
Give me an example.
Okay, maybe someone whose model shows a really high disutility, a strong negative reward, for travel time might receive more personalized incentives or information, encouraging them to use a faster, maybe slightly more expensive public transport option.
I see.
But maybe the more subtle, non-obvious idea here is that those interpreted M&L coefficients we talked about, they might reveal latent factors influencing choices that go beyond just standard demographics.
Like what?
Maybe certain ways of communicating policy benefits, certain framing effects, resonate more strongly with specific behavioral profiles identified by the model. So interventions could be tailored not just to what people do, but why they do it, maybe even down to the level of cognitive biases revealed through their sequential decision pattern.
Wow. So tailoring the message based on the inferred why.
Exactly.
Yeah.
It could lead to far more effective and maybe less intrusive interventions, helping optimize urban flow and potentially increasing user satisfaction because the policies feel more aligned with individual needs and preferences. Of course, this is speculative, for entertainment purposes only.
Naturally. That's a fascinating thought experiment, though. What's another novel research direction that comes to mind, maybe thinking bigger picture?
Okay, let's think about infrastructure planning. Right now, it's often quite reactive, right? Based on current or projected demand.
Usually, yeah.
What if we could make it more proactive? What if we could adapt infrastructure based on the evolving reward landscape of activity travel across the city?
The reward landscape, you mean the collective preferences?
Yeah, imagine using real-time mobility data streams from smartphones, connected vehicles, transit systems to continuously update these interpretable DIRL models. This would give us a dynamic, near real-time view of what activities and travel patterns are becoming more or less rewarding to the population as a whole.
So, the collective preferences, as learned by the AI in real time, could directly inform infrastructure decisions much more dynamically.
That's the obvious connection, yes. Significant shifts in the collective reward function, like, say, a rapid, sustained increase in the reward people seem to get from remote work, paired with a decrease for traditional commuting.
Like we saw during the pandemic.
Exactly. That could signal a clear need for proactive adjustments in transportation infrastructure planning. Maybe less investment in expanding highways for traditional commutes, and more investment in, say, last-mile connectivity in residential areas, or better support for local neighborhood hubs.
Makes sense. Is there a non-obvious angle there, too?
I think so. Maybe the rate of change in the reward function for certain activity sequences could serve as an early indicator of emerging social or economic trends.
An early warning system.
Kind of. For example, maybe a rapidly increasing reward associated with local errands, combined with a decreasing reward for trips to centralized shopping malls, might suggest a fundamental shift towards more localized economic activity, even before it shows up clearly in traditional economic data.
And infrastructure could anticipate that.
Infrastructure investment could then anticipate and actively support these evolving patterns, going beyond simply reacting to current demand figures. It builds on the core idea of using IRL to understand motivations, like in this paper, but scales it up to a dynamic, aggregate level for strategic infrastructure planning. It could potentially inform long-term urban development models in a much more responsive and forward-looking way. Again, just exploring ideas here.
Absolutely fascinating potential, though. It really underscores how these advanced machine learning techniques, especially when made interpretable, can give us a much deeper understanding of ourselves and the complex ways we interact with our urban environments. The key takeaway from this paper, though, is that we're gaining a powerful new lens, an interpretable one, for analyzing that intricate dance of our daily activities and travel decisions.
Yeah, it's a really promising direction.
And it holds significant promise, it seems, for creating more human-centric, more effective urban planning and transportation policies down the line.
Definitely.
If you're interested in digging into all the methodological details, the link to the full paper is, as always, in the show notes.
It's worth a read.
Thanks for joining us for this deep dive into the world of machine learning and human behavioral analysis.